Have you ever wondered what the universe quietly does while the rest of the world falls asleep? Hello, and welcome to the Quiet Universe channel. I'm so glad you're here tonight. Maybe it has been a long day. Maybe your thoughts are still moving when your body is ready to be still. Or maybe you simply like to drift towards sleep thinking about stars and deep time and the slow, patient mechanics of a cosmos that has been running for nearly 14 billion years without ever once stopping to rest. Whatever brought you here, tonight is for you. There is nothing you need to do right now. No problem to solve, no decision to make. Just let your body settle into wherever you are. Let your breathing find its own rhythm, and let your mind float gently outward. Past the ceiling, past the clouds, past the thin blue line of atmosphere that separates this room from the rest of everything. Tonight, we are going to move slowly through the universe together. We will visit black holes and ancient light and impossible distances and the quiet chemistry that happens between the stars when no one is watching. Some of these things may surprise you. Some may settle into you like a thought at the edge of sleep, felt more than understood. And if these calm journeys through the cosmos help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you are ready, let us begin. The universe might be older than we thought. The number most scientists use is 13.8 billion years. This comes from precise measurements of the cosmic microwave background, the faint all-sky glow left over from the Big Bang, and from careful observations of how fast space is expanding. These measurements are extraordinarily careful and extraordinarily consistent with each other, but not all methods agree perfectly. When astronomers measure the expansion rate using distant supernovae, they sometimes arrive at a slightly different number than when they measure it using the cosmic microwave background. When they date the oldest stars in the universe, some of those stars appear to be nearly as old as the universe itself, leaving very little margin for anything to have happened before they formed. These tensions have not been resolved. Most scientists are confident the 13.8 billion figure is close to correct, but the precise value is still actively debated. Some measurements hint at a slightly older universe. Others suggest the expansion rate may not be constant in the way our models assume. A few researchers have proposed that dark energy itself may have changed over cosmic time, which would alter every age calculation built on top of it. What if the universe is older than we know? What if the story began earlier, in conditions we cannot yet see? The universe keeps its oldest secrets in places our instruments have not yet reached. For now, 13.8 billion years. Give or take, a long time either way. There are thousands of planets drifting through space without any star. Not all planets orbit stars. Some were ejected from their solar systems long ago by gravitational interactions, a close encounter with a massive planet, a disruption from a passing star, a chaotic moment in the early history of a young planetary system. These planets were flung outward with enough velocity to escape their star's gravity entirely. Others may never have had a star at all. They may have formed on their own from collapsing clouds of gas and dust, too small to ignite nuclear fusion, but large enough to hold themselves together under their own gravity. These rogue planets drift through the dark spaces between stars, completely alone. No sun rises over them, no seasons change. No light falls on their surfaces except the faint, combined glow of a billion distant stars, indistinguishable from perfect darkness. If they have atmospheres, those atmospheres are probably frozen. If they have oceans, those oceans are probably ice, pressed deep under rock. Some may have warm interiors, heated by radioactive decay in their cores, the way Earth generates its own internal heat. Beneath a frozen surface, in the warmth of the planet's own geology, liquid water might theoretically exist. Whether anything lives there in the dark beneath the ice, orbiting nothing, warmed only by the slow decay of ancient atoms. This is one of the questions that current science cannot answer. There may be more of these rogue planets than there are stars in the Milky Way. They are nearly impossible to detect, invisible, except when they happen to pass in front of a background star. Most of them will drift through the galaxy forever, silent and alone, never encountered by anything. The universe contains a kind of light you will never see. Human vision detects a narrow slice of the electromagnetic spectrum, wavelengths between approximately 380 nanometers on the violet end and 700 nanometers on the red end. This range is what we call visible light, and it encompasses every color you have ever seen. But the electromagnetic spectrum extends far beyond this narrow band in both directions. Just below red is infrared radiation, heat. You feel it from the sun on your skin, and some animals can see it. Below infrared is microwave radiation used in ovens and in cellular communications. Below that is radio, which carries broadcasts across continents and signals between spacecraft. Above violet is ultraviolet, which causes sunburn and is blocked by Earth's ozone layer. Above ultraviolet is X-ray radiation, which passes through soft tissue but is blocked by bone. And above X-rays is gamma radiation, which carries enough energy per photon to damage DNA. Every object in the universe emits radiation across this spectrum in patterns that depend on its temperature, composition, and physical processes. The sun emits predominantly in the visible and near infrared. Very hot gas around black holes emits X-rays. Exploding stars emit gamma rays. The cosmic microwave background, the oldest light in the universe, emits at wavelengths your microwave oven also uses. When radio astronomers point their dishes at the sky, they hear a universe completely invisible to human eyes, pulsars ticking with extraordinary regularity, galaxies with jets of plasma, millions of light years long, the faint cosmic static of the earliest moments of existence. You are surrounded by light you cannot see. It passes through the walls of this room. It comes from ancient events billions of light years away. The universe is speaking in frequencies your eyes were not built to receive. The oldest light in the universe is everywhere right now. It is not somewhere distant. It is here, in this room, passing through the walls, through the air, through you. 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was an opaque fog, a plasma so dense that photons could not travel more than a tiny distance before being scattered. Light was trapped. When the atoms formed, the fog cleared. For the first time in cosmic history, light could travel freely. The photons that had been trapped in the plasma burst outward in all directions simultaneously, flooding the newly transparent universe with light. Those photons have been traveling ever since. In the 13.4 billion years since their release, the universe has expanded enormously. That expansion has stretched the wavelengths of the photons, cooling them from the hot glow of the early plasma to the faint microwave warmth they carry today, approximately 2.7 degrees above absolute zero. This is the cosmic microwave background. It fills all of space in every direction, arriving from everywhere at once. In this room right now, approximately 411 of these ancient photons pass through every cubic centimeter every second. They travel through the walls, through your body, through the floor and the earth below it, continuing outward on the other side. The oldest light in the universe is not in a telescope image. It is not in an observatory somewhere. It is here with you now, as it has always been, a quiet presence from the beginning of everything. Some stars orbit the center of the Milky Way backward. Most stars in the Milky Way orbit the galactic center in the same general direction. following the rotation of the galaxy, sweeping around in a vast counterclockwise motion when viewed from above. This makes intuitive sense. The galaxy formed from a rotating cloud of gas, and most of the stars that formed within it inherited that rotation. But not all of them. Some stars move in the opposite direction, orbiting the galactic center in retrograde, against the flow, like a salmon swimming upstream in a river of billions. One well documented example is a star designated HA 130444, a main sequence star orbiting the Milky Way in a retrograde orbit with unusual chemical composition. How do such stars come to be? The most likely explanations is that they were once members of smaller galaxies that merged with the Milky Way long ago. When galaxies collide and merge, the stars of the smaller system do not necessarily align themselves with the rotation of the larger one. Depending on the angle of approach and the dynamics of the merger, some stars end up in retrograde orbits that persist for billions of years. The Milky Way has consumed many smaller galaxies throughout its history. The evidence is preserved in the stellar halo, the sparse cloud of old stars surrounding the visible disk, where groups of stars with matching orbits and chemical compositions tell the stories of galaxies that no longer exist as separate objects, absorbed and blended into the one we call home. The retrograde stars are their legacy, moving against the current, carrying the memory of a journey that began in another galaxy entirely. There is a sound from the beginning of the universe still written in the sky. In the first 380,000 years after the Big Bang, before the universe became transparent, the hot plasma that filled all of space was not perfectly still. It was vibrating. Gravity was pulling matter together, trying to compress the plasma into denser regions. But the intense radiation pressure of the trapped light was pushing back, resisting compression. The result was acoustic oscillations, pressure waves moving through the plasma at about 57% of the speed of light. These were the universe's first sounds, propagating through the primordial medium in every direction. When the plasma cooled into atoms and light was released, those pressure waves froze in place. The matter they had been moving could no longer respond to the radiation pressure. The oscillations stopped. Their final positions were imprinted in the distribution of matter across space. Today, billions of years later, this ancient sound is still visible. Galaxies are not randomly distributed. They show a slight statistical preference for being separated by a specific distance, approximately 500 million light years, corresponding to the distance. Those pressure waves traveled in the 380,000 years before the universe became transparent. This phenomenon is called baryon acoustic oscillations. It is the acoustic record of the universe's earliest vibrations, preserved in the cosmic large-scale structure like the rings of a tree that remember every year of its growth. The first sound ever made is written in the arrangement of galaxies across the sky. No instrument can play it, but mathematics can read it. Dark matter streams through your body as you rest. Right now, as you lie still, dark matter is passing through you, through the mattress, through the floor, through the earth, through you, and out the other side, without interacting with a single atom in any of these things. Dark matter is the name we give to whatever it is that accounts for approximately 27% of the universe's total mass energy content. We know it exists because of its gravitational effects. Galaxies rotate faster than they should if they contained only visible matter. Light from distant galaxies bends more than it should when passing through galaxy clusters. The structure of the cosmic web could not have formed the way it did without an invisible scaffolding of mass that does not emit, absorb, or reflect light. But no instrument has directly detected a dark matter particle. The most sensitive detectors ever built tanks of ultra-pure liquid xenon buried kilometers underground, cooled to temperatures a fraction of a degree above absolute zero, have run for years listening for a signal that has not come. The parameter space of the most popular theoretical candidates has been largely ruled out. Dark matter passes through ordinary matter almost completely without interaction. The Milky Way's dark matter halo, a vast sphere surrounding the visible galaxy, is not separate from the galaxy. It interpenetrates it. Dark matter is here in this room, moving through the walls and the furniture and in your body at a speed of approximately 220 kilometers per second relative to the Earth. Something is here with you tonight, has always been here, and cannot be felt or seen or heard. Its presence is known only through the gravity it exerts on the things we can see. Some galaxies are almost entirely dark matter. Most galaxies are a mixture of visible matter and dark matter, with dark matter typically outweighing visible matter by a factor of 5 or 10 to 1. The stars and gas we can see are embedded in a much larger dark matter halo, and the two components together determine how the galaxy forms and evolves. But some galaxies are almost entirely dark matter. They contain very few stars, sometimes fewer than would fill a modest star cluster, despite occupying a region of space as large as a normal galaxy. Their dark matter content is enormous. Their visible matter content is nearly nothing. These are sometimes called ultra-faint dwarf galaxies, and some of them have been found orbiting the Milky Way. SEG 1, for example, appears to have a mass-to-light ratio, the ratio of total mass to the mass in visible stars, of approximately 3,400 to 1. For every unit of light-producing matter, there are 3,400 units of dark matter. How they formed, why they contain so little visible matter, and why the dark matter failed to collapse into stars, as it does in more normal galaxies, are open questions. They may be failed galaxies, structures that began to form, collapsed into dark matter halos, but for some reason never accumulated enough gas to form a substantial stellar population. Or they may have formed stars early in cosmic history and then lost them to tidal stripping as they orbited larger galaxies. They are ghosts of galaxies, held together by invisible mass, almost entirely without light. There are stars that have been burning since before the Earth existed. The Sun is approximately 4.5 billion years old. It formed when a cloud of interstellar gas and dust collapsed under its own gravity, igniting nuclear fusion in its core. Before that collapse, the material that forms the Sun had been part of the interstellar medium, enriched by multiple generations of stellar evolution and stellar death. But some stars are much older. Stars with lower masses burn their hydrogen much more slowly than the Sun. A star with half the Sun's mass burns its hydrogen at such a leisurely pace that it can remain on the main sequence, fusing hydrogen to helium in its core for 100 billion years or more. The universe is only 13.8 billion years old. No such star has yet come close to exhausting its fuel. The oldest stars in the universe formed within the first few 100 million years after the Big Bang, from the pristine hydrogen and helium that the Big Bang nucleosynthesis produced. These stars have been burning continuously ever since. Some of them are in our galaxy, in the halo, and in old globular clusters, visible through a small telescope on a dark night. They have been shining for longer than the Earth has existed, longer than the Sun has existed, longer than most of the heavy elements in the universe have existed. They carry the chemical record of the early cosmos. Their atmospheres contain almost no carbon, no oxygen, no iron, elements that did not yet exist when they formed. Every heavy element in the universe, heavier than lithium, was forged afterward in stars that formed later, lived and died, and scattered their contents into the galaxy. These old stars saw none of that. They formed before any of it happened. They are still here. The universe may cycle through endless expansions and collapses. The standard cosmological model describes a universe with a definite beginning, the Big Bang, and an indefinite future of expansion. Under the influence of dark energy, space will continue expanding forever. Galaxies will drift apart, stars will burn out, and the universe will gradually approach the cold, dark, diffuse state that physicists call heat death. But this is not the only possibility that theoretical cosmology has considered. Some models propose that the universe undergoes cycles. After reaching a state of maximum expansion and minimum density, some mechanism causes the expansion to reverse, a big crunch that mirrors the Big Bang in reverse. But rather than collapsing to a point and ending, the matter and energy bounce back outward in a new Big Bang, beginning a new cycle of expansion. Each cycle could produce a different universe with different constants of physics, different structures, different histories. More recent cyclic models, developed by Paul Steinhardt and Neil Turok and others, involve the collision of higher dimensional surfaces called branes, with our observable universe being one such surface. In these models, the cycles are not the collapse and rebirth of a single universe, but the periodic encounters between the surfaces, each encounter producing what we perceive as a new Big Bang. These models are speculative. There is currently no observational evidence that clearly distinguishes them from the standard single expansion model. But they are not idle fantasy. They are mathematically rigorous proposals that make specific predictions, some of which future observations might test. The universe may have a past that extends before the Big Bang. It may have gone through countless previous cycles, each producing a cosmos of its own. What we call the beginning may be only the most recent beginning in an infinite series. Some stars eat their companions, which many stars exist not alone but in pairs, orbiting each other in a binary system. Depending on their mass and the distance between them, these binary partners can live in apparent harmony for billions of years, each evolving independently, each tracing its own path through stellar life. But sometimes one star evolves faster than the other. When a more massive star expands into a red giant, its outer layers may extend far enough to reach the gravitational sphere of influence of its companion. Gas from the giant's outer atmosphere begins to stream across the space between them, falling onto the smaller star. The smaller star is gaining mass, accreting it from its partner, slowly consuming what was once a separate world. This process can have dramatic consequences. The accreting star can become unstable, pulsing in brightness or erupting in novae, explosions on its surface caused by the buildup of freshly accreted hydrogen that ignites in a sudden thermonuclear flash. If the accreting object is a white dwarf and the accumulated mass exceeds a critical threshold, the entire white dwarf can detonate in a Type Ia supernova, one of the most powerful explosions in the universe, briefly outshining its entire host galaxy. These cannibal stars are not rare. Perhaps 1 in 3 binary systems will experience significant mass transfer at some point in their lifetimes. The universe is full of pairs in which one partner is slowly consuming the other, gram by gram across the centuries, in a process so slow it is invisible on human timescales, but unmistakable across millions of years. Time moves more slowly near massive objects. This is not metaphor. It is not philosophy. It is a measurable, confirmed prediction of Einstein's general theory of relativity. Gravity does not merely attract matter, it curves space-time itself, the four-dimensional fabric in which all events occur. Near a massive object, where gravity is strong, space-time is more curved. And in more curved spacetime, time passes more slowly relative to regions of weaker gravity. This effect has been measured directly on Earth. Clocks at higher altitudes, further from Earth's center, in regions of slightly weaker gravity, run faster than clocks at lower altitudes. The difference is tiny by everyday standards, but it is real and it must be corrected for in the GPS satellite network, which depends on atomic clocks. Without the correction, GPS navigation would accumulate errors of several kilometers per day. Near a neutron star, where gravity is enormously stronger than on Earth, the time dilation is significant. Time passes more slowly on the surface of a neutron star by a factor of approximately 30 to 40% compared to an observer far away. A clock on the surface would lose approximately 30 to 40% of its ticks compared to a clock in distant space. Near a black hole, the effect becomes extreme. At the event horizon, the point of no return, time from the perspective of a distant observer appears to stop entirely. An object falling toward the event horizon, watched from far away, appears to slow and redden and dim, frozen at the horizon for an infinite time from the outside observer's perspective, while from the falling object's own perspective, it crosses the horizon in finite time and continues inward. Time is not a universal clock ticking at the same rate everywhere. It bends, it stretches, it slows in the presence of mass. The universe keeps different times in different places. There is a chemical factory in the space between the stars. The space between stars is not empty in any meaningful chemical sense. It contains gas, mostly hydrogen and helium and dust, tiny grains of carbon and silicates, coated in ice, drifting slowly through the cold dark. And on the surfaces of those ice-coated grains, chemistry is happening. Ultraviolet radiation from distant stars strikes the ice, energizing chemical reactions. Cosmic rays, high energy particles accelerated by supernovae and other violent processes, penetrate the clouds and break chemical bonds, creating reactive fragments that recombine in new configurations. The temperatures are extreme, as cold as minus 263 degrees Celsius in the densest clouds, and the densities are almost unimaginably thin. But time compensates for what physics makes slow. In these molecular clouds, astronomers have detected over 200 different chemical species. Simple molecules, water, carbon monoxide, ammonia, formaldehyde; more complex ones, methanol, ethanol, acetic acid, glycolaldehyde, a simple sugar; amino acid precursors, the building blocks of RNA. These molecules are not found because they are rare, but because they are common. Everywhere astronomers have looked in cold molecular clouds, they have found organic chemistry in progress. The universe does not reserve organic chemistry for warm, lit, life-bearing planets. It runs that chemistry in the frozen dark between the stars, in conditions where nothing that we know of could live. When planetary systems form from these clouds, the organic chemistry comes with them. Comets and asteroids, assembled from the same molecular cloud material, carry these molecules to young planets, delivering them in the first billion years of the solar system's history. The organic inventory of life may not have originated on Earth. It may have arrived from interstellar space, already assembled by the patient chemistry of the molecular clouds. Every element in your body was made in a star. The hydrogen in the water in your cells was made in the Big Bang, the lightest and oldest element forged in the first 3 minutes of cosmic history from the quarks and gluons of the initial plasma. It has never been processed through a star. It arrived in the molecular cloud that formed the solar system exactly as the Big Bang left it, 13.8 billion years old. But the other elements, the carbon, the oxygen, the nitrogen, the phosphorus, the sulfur that form the backbone of your biochemistry, were made inside stars. Carbon and oxygen are synthesized in the helium-burning phase of sun-like stars and more massive ones through a sequence of nuclear reactions that runs from helium to carbon and then from carbon to oxygen. These elements are expelled into the interstellar medium when the star dies, either gently in the slow stellar winds of an aging red giant or violently in a supernova. The iron in your blood is different. Iron is the end product of nuclear burning in massive stars. It is the most tightly bound nucleus in nature. Fusing iron releases no energy, so when a massive star's core becomes iron, the fusion stops. The core collapses catastrophically in less than a second. The outer layers of the star detonate in a core collapse supernova. The calcium in your bones, the sodium in your nerves, the potassium in your cells, all made in stars, all scattered by their deaths, all drifting through interstellar space for millions or billions of years before being gathered into the molecular cloud that collapsed to form the sun and its planets. You are the universe looking at itself. Every atom of you was forged in the nuclear furnace of a star that died before you were born. There are galaxies that appear to have no dark matter at all. Dark matter is supposed to be everywhere. It forms the scaffolding of the cosmic web. It is the invisible framework into which visible matter falls to form galaxies and galaxy clusters. Without it, the universe's structure would look completely different from what we observe. Every galaxy should be embedded in a dark matter halo containing several times more mass than the visible stars and gas. But in 2018, astronomer Pieter van Dokkum and colleagues published a paper in Nature reporting the discovery of a galaxy called NGC 1052DF2, which appeared to contain almost no dark matter. The galaxy's stars were moving as if only visible matter were present. The dark matter signal was absent. The discovery was controversial. Some astronomers questioned the distance estimate, arguing that if the galaxy were closer than estimated, the apparent absence of dark matter would be explained. Others proposed that dark matter had been stripped away by gravitational interactions with a nearby massive galaxy. Van Dokkum and his teams subsequently found additional examples of galaxies apparently lacking dark matter. Whether these galaxies truly lack dark matter, or whether they have had it stripped away, or whether our measurement techniques have failed in some subtle way remains actively debated. But the possibility that galaxies can exist without dark matter, if confirmed, would require a significant revision in our understanding of how galaxies form. The universe may not follow the rules we have derived for it as consistently as we assumed. Some systems may find ways to exist outside the standard model of galaxy formation. The exceptions are often where the most important lessons hide. Some black holes are primordial, older than any star. Most black holes in the universe today formed from the collapse of massive stars. When a star with more than approximately 20 times the mass of the Sun exhausts its nuclear fuel, its core collapses and cannot be supported by any known pressure. The collapse continues until a black hole forms. But there is another class of black hole that some theorists have proposed: primordial black holes, formed not from stellar collapse but from density fluctuations in the very early universe, within the first fraction of a second after the Big Bang. In the extreme conditions of the early universe, regions of slightly higher density could in principle collapse directly into black holes before any stars existed. Depending on when in the early universe they formed, these primordial black holes could range enormously in mass, from objects smaller than the moon to objects with billions of solar masses. Some of the supermassive black holes at the centers of the earliest observed galaxies, massive objects seen when the universe was only a few 100 million years old, may be too large to have grown from stellar black holes in such a short time. Primordial origins have been proposed. No primordial black hole has been definitively identified. Their detection would require either gravitational microlensing signatures for small ones or matching patterns of gravitational wave emissions for merging ones. The search is active. The detection would resolve a long-standing puzzle about where dark matter may actually reside. since some models suggest primordial black holes could constitute some or all of the dark matter. Somewhere in the history of the universe, in the first fraction of a second, the seeds of some of the largest structures we know may have been silently planted. My, there may be more planets in the universe than there are grains of sand on all of Earth's beaches. Let us think about what that comparison requires. Astronomers estimate that the total number of grains of sand on all of Earth's beaches and deserts approximately 10 to the 19th 10 billion. That is already a number difficult to hold in the mind. But the observable universe appears to contain roughly 2 trillion galaxies, each containing on average approximately 100 billion stars. That gives approximately 2 times 10 to the 23rd power stars in the observable universe. The Kepler Space Telescope, which observed a small patch of sky for 4 years and measured thousands of planet transits, gave astronomers the statistical tools to estimate the average number of planets per star. The results suggest that most stars host at least one planet, with many hosting several. Small rocky planets appear to be especially common, more common than gas giants. The average number of planets per star across the galaxy may be greater than one. If the average is even one planet per star, across all of the observable universe, the total number of planets is approximately 2 times 10 to the 23rd power, roughly 10,000 times the estimated number of sand grains on Earth. Each of those planets is a world, a surface, a place where conditions are some specific combination of temperature, pressure, radiation, and chemistry unlike any other combination in the universe. Most are probably inhospitable to life as we know it. Some may not be. The number of potentially habitable worlds, even if only a tiny fraction of all planets qualify, is staggeringly large. We have confirmed the existence of only a few thousand of these worlds. We have directly studied the surfaces of 4: the Moon, Mars, Venus briefly, and Earth. The rest remain in the dark, each one a mystery, waiting. There is a star that may be larger than anything our intuition can hold. The largest stars known are called hypergiants, and they push the boundaries of what stellar physics permits. Stars do not simply grow indefinitely. There is an upper limit imposed by radiation pressure. As a star becomes more luminous, the outward pressure of its own radiation increasingly opposes the inward pull of gravity. Stars above approximately 150 solar masses are so luminous that radiation pressure begins to blow their outer layers away, preventing further growth. Despite this limit, some stars exist near and possibly beyond it. Uy Scuti, a hypergiant in the constellation Scutum, has a radius estimated at approximately 1,700 solar radii. If Uy Scuti were placed at the center of the solar system, its surface would extend past the orbit of Jupiter. Not the orbit of Earth, the orbit of Jupiter. The volume it would occupy would swallow all 4 of the inner rocky planets, the asteroid belt, and the gas giant Jupiter, with room to continue expanding towards Saturn. The Sun, placed inside Uy Scuti, would be invisible to the naked eye, a point of light lost inside a sphere too large for comprehension. These hypergiants are not stable. They pulsate, varying in size and brightness over months and years. They shed mass continuously, blowing their outer layers into space in dense stellar winds. They live for only a few million years, the cosmic equivalent of a mayfly, before exhausting their fuel and ending in a supernova or collapsing directly into a black hole. The universe makes objects of such extreme scales that the numbers lose their power to convey meaning. They require something else, not calculation, but surrender to incomprehension. There is a molecule in space that smells of raspberries and rum. This is not a metaphor. Astronomers studying the chemical composition of the molecular cloud Sagittarius B2 near the center of the Milky Way discovered ethyl formate, An organic ester that on Earth is associated with the flavor of raspberries and the scent of rum. It formed in the cold, dense gas of the molecular cloud through a series of chemical reactions involving ice coated dust grains and energetic radiation. This discovery is part of a broader picture. The interstellar medium, particularly in cold molecular clouds, is chemically extraordinarily rich. Over 200 different molecular species have been identified in space. Among them are complex organic molecules, alcohols, aldehydes, ketones, sugars, amino acid precursors. The chemistry that life depends on is not confined to planets. It runs in the spaces between stars, in conditions of extreme cold and extreme dilution, driven by the patient action of radiation and time. This matters because it suggests that the molecular building blocks of life do not need to originate on a planet. They may arrive on planets from outside, delivered by comets and asteroids that formed in the same molecular clouds where interstellar chemistry was running. The organic chemistry of life may have begun in the interstellar dark long before any particular planet existed. The universe does not need a warm, lit, hospitable environment to make organic molecules. It makes them in conditions that would kill every living thing we know of. The production is automatic, universal, and ancient. There is a region of the universe called the cold spot that should not exist. The cosmic microwave background, the ancient light from 380,000 years after the Big Bang, fills the sky in every direction. When astronomers map its temperature across the full sky, it is remarkably uniform. The variations from region to region are typically less than 1 part in 100,000. The smoothness is itself a profound fact about the early universe. But there is one region in the southern sky, centered on the constellation Eridanus, where the temperature is significantly colder than the surrounding average. Not slightly colder, and significantly larger than the statistical analysis of cosmic microwave background fluctuations predicts. This is the CMB cold spot. Various explanations have been proposed. The most straightforward is a vast cosmic void, a region with significantly below average density of matter, whose gravitational properties would produce the cooling signature through a subtle effect called the integrated Sachs-Wolf effect, in which photons lose energy traversing the expanding void. A survey of galaxies in the region does show evidence of a large underdense void, though whether it is large enough and empty enough to fully explain the cold spot is debated. Some researchers have proposed more exotic explanations, the imprint of a collision between our universe and another in the multiverse during the era of cosmic inflation. This would be a direct observational signature of the multiverse. It would make one of the most consequential measurements in the history of cosmology. Whether the cold spot is a statistical fluctuation, a cosmic void, a collision scar from another universe, or something else entirely, it remains one of the most quietly unresolved puzzles in modern cosmology. The moon is slowly leaving us. Every year, the moon drifts approximately 3.8 centimeters farther from Earth. That is roughly the rate at which your fingernails grow. Over a human lifetime, the moon moves farther away by about 3 meters. You will never notice. No instrument you can hold in your hands could detect it. But over geologic time, the effect is substantial. The cause is tidal friction. The moon's gravity raises tides in Earth's oceans. As Earth rotates beneath the tidal bulge, friction gradually slows Earth's rotation. Days are getting longer at approximately 1.4 milliseconds per century. The angular momentum lost from Earth's rotation must go somewhere, and it goes into the moon's orbit, pushing it to a slightly larger radius. Energy is conserved, angular momentum is conserved, and the moon moves away. When the moon formed approximately 4.5 billion years ago, probably from the debris of a collision between the early Earth and a Mars sized body, it was much closer, perhaps 15 times closer than it is today. At that distance, it would have appeared enormous in the sky. Tides on the young Earth would have been far more powerful. Days would have been only a few hours long. Over billions of years, the moon will continue drifting outward and Earth's rotation will continue slowing. Eventually, in approximately 50 billion years, long after the sun has expanded and consumed the Earth, the two bodies would become tidally locked to each other, each always showing the same face to the other, rotating and orbiting in perfect synchrony. The moon is slowly saying goodbye. It is in no hurry. Neither are we. There is a type of star that spins faster than a kitchen blender. Neutron stars are the collapsed remnants of massive stars that have died in supernova explosions. When the core of a massive star collapses, the protons and electrons of ordinary matter are crushed together into neutrons, forming an object typically about 20 kilometers across with a mass greater than the sun. At this density, the laws of physics become unlike anything in ordinary experience. The neutrons are packed together as tightly as the nucleus of an atom. A teaspoon of neutron star material would weigh approximately 10 billion tons on Earth. The gravity at the surface is approximately 200 billion times Earth's surface gravity, and they spin. When the core of a star collapses to a neutron star, it shrinks enormously, from thousands of kilometers across to about 20 kilometers. By the conservation of angular momentum, this shrinkage causes an enormous increase in rotation rate. In the same way a spinning ice skater speeds up when drawing in their arms. A collapsing core that was rotating slowly becomes a neutron star that may be rotating hundreds of times per second. The fastest spinning neutron stars known are called millisecond pulsars. The current record holder, Popper J 1748 2446, rotates 716 times per second. At its equator, the surface is moving at approximately 24% of the speed of light. These objects are the most precisely ticking clocks in the universe. The regularity of their pulses rivals the best atomic clocks on Earth. Astronomers use them as tools for detecting gravitational waves, probing the interiors of neutron stars, and testing the predictions of general relativity in the most extreme gravitational fields accessible to observation. The space between galaxies is emptier than any vacuum humans have ever created. Between galaxies, in the vast voids of the cosmic web, far from any filament or cluster, the density of matter approaches values that seem impossible by any laboratory standard. In a good laboratory vacuum on Earth, the air is pumped out to leave approximately 100,000 million particles per cubic centimeter. This sounds like a lot, and it is, compared to the near total emptiness of space. But even in the thinnest regions of the interstellar medium within the Milky Way, there is approximately one atom per cubic centimeter. The best laboratory vacuum is still 100 billion times denser than typical interstellar space, but the intergalactic voids are emptier still. In the large voids between the filaments of the cosmic web, the average density of matter is approximately 100 to 1,000 times below the cosmic mean. The cosmic mean itself corresponds to only a few hydrogen atoms per cubic meter. The voids are measured in atoms per tens of cubic meters. If you were somehow transported to the middle of the Bootis void, one of the largest known voids, approximately 300 million light years across, you would find yourself in a region where the nearest galaxy in any direction was roughly 100 million light years away. The density of matter around you would be so low that atoms would be separated, on average, by distances far exceeding the best vacuum ever achieved in any physics laboratory. The universe at its emptiest is more empty than empty. The intergalactic voids are the true silence, not the silence of sound, which requires only the absence of pressure waves, but the silence of matter, the near total absence of anything at all. There are stars older than the galaxy that contains them. The Milky Way formed gradually, assembling from smaller structures over billions of years through mergers and gravitational accretion. It did not appear fully formed at any single moment. It has been building itself continuously since early in cosmic history, but some of the stars within it are older than the galaxy's current structure. When smaller protogalaxies, the first condensations of gas and dark matter in the early universe, collided and merged with each other to build the Milky Way, they brought their stars with them. Those stars continued to orbit within the growing galaxy, eventually becoming part of the halo of old stars that surrounds the visible disk. Some of these stars date to within a few 100 million years of the Big Bang. Their chemical compositions reflect the conditions of the very early universe. Almost no heavy elements, just the hydrogen and helium of primordial nucleosynthesis, with traces of lithium. They formed in a universe that had not yet produced enough stellar generations to enrich the interstellar medium with carbon, oxygen, or iron. To look at such a star in a telescope is to look at a nearly direct product of the Big Bang. The material in its atmosphere has not been significantly altered in 13 billion years. It carries the chemical signature of the universe's first structures, preserved in its light across cosmic time. These ancient stars are still burning. They will continue burning for billions of years to come. In their patience and their antiquity, they are unlike anything else in nature. There is a limit to how far we can ever see, and it is getting smaller. The observable universe is defined by the speed of light and the age of the universe. Light has had time to reach us from objects up to approximately 46.5 billion light years away. Beyond that distance, the light has not yet arrived, but the expansion of the universe is accelerating. Driven by dark energy, the most distant galaxies are receding from us at faster than the speed of light, not because they are moving through space faster than light, which is impossible, but because the space between us and them is expanding. Their recession velocity, produced by expanding space, can exceed the speed of light without violating any physical law. This means that light from the most distant galaxies we can currently see is the last light we will ever receive from them. From this moment forward, those galaxies are moving faster than their light can close the gap. They are crossing the cosmic event horizon, the boundary beyond which no future signal from them can ever reach us. Galaxies are disappearing from our observable universe, not because they are destroyed, but because the expanding universe is carrying them beyond the reach of our light. Over hundreds of billions of years, more and more of the universe's galaxies will cross this horizon. The sky, viewed from a civilization a trillion years from now, will be almost empty. Only the local group of galaxies will remain visible, a tiny island in an apparently infinite void. The universe is not just expanding, it is hiding. The portion of it accessible to observation is shrinking over time, as the accelerating expansion carries more and more of reality beyond the horizon. There are places in the universe where a day lasts longer than a year. This is not an impossible riddle. It is a description of Venus. Venus orbits the Sun in approximately 224.7 Earth days. This is the Venusian year, the time it takes to complete one orbit. But Venus rotates on its axis extremely slowly, so slowly that a single Venusian day, from one sunrise to the next sunrise, as measured on its surface, takes approximately 117 Earth days. It also rotates in the opposite direction from most planets, so the sun rises in the west and sets in the east. The result, a year on Venus is shorter than a day on Venus. The planet completes more than two full orbits of the sun in the time it takes to complete a single rotation. Why Venus rotates so slowly and in the wrong direction is not fully understood. One leading theory involves tidal interactions with the Sun and with the thick Venusian atmosphere, which may have gradually braked and then reversed the rotation over billions of years. Another involves a giant impact early in the solar system's history. Venus also has a surface temperature of approximately 465 degrees Celsius, hot enough to melt lead, caused by a runaway greenhouse effect. The atmospheric pressure at the surface is about 90 times Earth's. The clouds are made of sulfuric acid. The solar system, even in its familiar inner region, contains worlds that follow rules utterly unlike our own. There are objects so dense that a single teaspoon of their material weighs more than all the humans who have ever lived. The material inside a neutron star is the densest matter in the known universe that is not a black hole. The density is approximately 10 to the 17 power kilograms per cubic meter, 10 followed by 17 zeros. In more intuitive terms, approximately 3 billion tons per cubic centimeter. The total mass of all humans who have ever lived, approximately 108 billion people over the course of human history, averaging perhaps 60 kilograms each, is approximately 6.5 times 10 to the 12th power kilograms, 6.5 trillion kilograms. A single teaspoon, about 5 cubic centimeters, of neutron star material weighs approximately 15 billion tons, or approximately 1.5 times 10 to the 13 power kilograms. That is more than twice the mass of all humans who have ever lived in an amount of material that would fit in a small spoon. This density is achieved because the neutrons in a neutron star are packed together as tightly as the neutrons in an atomic nucleus. In ordinary matter, atoms are mostly empty space. The electrons orbit far from the tiny nucleus, separated from it by distances enormous relative to the nucleus itself. In a neutron star, all of that empty space has been crushed away. What remains is nuclear density all the way through. The physics of such dense matter is not fully understood. The equations of state, the relationships between pressure, density, and temperature, are active areas of research. Gravitational wave observations of neutron star mergers, like the one detected in 2017 simultaneously in gravitational waves and light, are beginning to constrain these equations by measuring the sizes and masses of neutron stars directly. There is a temperature the universe will approach but never quite reach. Absolute zero, 0 Kelvin, approximately minus 273 degrees Celsius, is the theoretical minimum temperature. At absolute zero, all thermal motion would cease. No heat energy would remain. Quantum mechanics prevents this from ever being achieved exactly. Even at the lowest possible temperatures, quantum fluctuations persist. The uncertainty principle ensures that no particle can be simultaneously at rest and in a defined position. So a residual zero-point energy always remains. The universe is currently cooling. The cosmic microwave background, the oldest light in the universe, now cooled to microwave wavelengths by the expansion of space, has a temperature of approximately 2.7 degrees Kelvin. It is slowly getting colder as space continues to expand and stretch the wavelengths of these photons further. In a trillion years, the temperature of the background radiation will be a fraction of its current value. In 10 trillion years, smaller still. Over the timescales associated with the end of the stelliferous era, when the last stars burn out and the universe goes dark, the background will have cooled to something like 10 to the minus 9 Kelvin, a billionth of a degree, but not zero. Quantum mechanics will not permit it. However long the universe cools, however dim the background becomes, a residual quantum warmth will persist, unmeasurable in practice, but real in principle. The universe will approach silence. It will never quite achieve it, light does not age. This statement requires explanation because it seems to contradict everything we know about light traveling for billions of years and arriving worn and stretched by the expansion of the universe. From our perspective, light does age in the sense that it is stretched by cosmic expansion, redshifted from visible wavelengths to infrared to microwave as the universe grows. But from the photon's own perspective, which is a physically well defined concept in special relativity, even if strange to contemplate, no time passes. A photon travels at the speed of light. Special relativity tells us that time dilation is maximal at the speed of light. In the reference frame of a photon, time does not advance at all. The photon experiences no duration between its emission and its absorption. This means that a photon emitted by a star 13 billion light years away and absorbed by a detector on Earth has, from the photon's perspective, made an instantaneous journey. The 13 billion years that passed in our reference frame did not exist in the photon's reference frame. There was emission. Then, with no subjective interval, there was absorption. The entire history of cosmic expansion between those two events, the formation of galaxies, the evolution of stars, the emergence of life, all of it occurred in the 0 seconds that elapsed for the photon. The ancient light that fills our telescopes is not old from the light's point of view. It is exactly as fresh as the moment it was made. The age belongs to us, to the universe, to everything between the emission and the reception, not to the light itself. There is a giant hole in the universe that should not be there. In 2007, astronomers analyzing data from the WMAP satellite, a space observatory mapping the cosmic microwave background in detail, found something unexpected. A circular region of the CMB about 10 degrees across in the direction of the constellation Eridanus was significantly colder than the surrounding average. More than expected, more than the standard model of cosmology predicts for any randomly occurring fluctuation. This became known as the CMB cold spot. A subsequent survey of galaxies in that direction found evidence of a large void, a region of the universe with significantly below average density of galaxies, roughly 1 billion light years across. Whether this void is large and empty enough to explain the cold spot is still debated. The alternative explanations are more exotic. Some physicists have proposed that the cold spot is the imprint of a collision between our universe and another universe during the period of cosmic inflation, a direct observable scar from a multiverse event. The specific pattern of temperature variation that such a collision would produce has been calculated, and the CMB cold spot bears some resemblance to it. This would make the cold spot the first observational evidence for the multiverse, a region of the sky where another universe briefly touched ours, leaving a permanent mark in the oldest light we can see. Most cosmologists remain skeptical. The statistical significance of the cold spot has been debated, and the void explanation remains viable. But the possibility has not been ruled out. The quietest region of the oldest light we possess may be a scar from a collision with another cosmos. There are stars at the center of the galaxy orbiting a black hole at a significant fraction of the speed of light. Sagittarius A star, the supermassive black hole at the center of the Milky Way, with a mass approximately 4 million times that of the Sun, is surrounded by a dense cluster of young, massive stars. These stars orbit the black hole in tight, fast orbits that allow astronomers to precisely measure the black hole's mass and test general relativity in the strong field regime. The star S2, one of the most closely watched, has an orbital period of approximately 16 years and an orbital radius at closest approach, periapsis, of approximately 120 astronomical units from the black hole. One astronomical unit is the distance from Earth to the Sun. S2 at its closest is about 120 times farther from the black hole than Earth is from the Sun. At periapsis, S2 moves at approximately 7,000 kilometers per second, approximately 2.4% of the speed of light. This is fast enough that the effects of special and general relativity are measurable in the star's light. The orbit does not simply close into an ellipse, as Newtonian gravity would predict. It precesses. The point of closest approach rotates around the black hole, exactly as general relativity predicts for a mass of 4 million solar masses. Reinhard Genzel and Andrea Ghez, who led the two competing groups that spent decades tracking the orbits of these central stars and used them to determine the mass of Sagittarius A star, shared the Nobel Prize in Physics in 2020 for this work. 3 years later, the Event Horizon Telescope produced the first direct image of Sagittarius A star's shadow, the silhouette of the event horizon against the glowing ring of hot gas surrounding it. The black hole at the center of our galaxy has been confirmed, mapped, and photographed. It is there, 4 million solar masses, 26,000 light years away, with stars flying around it at thousands of kilometers per second. There may be more universes than there are atoms in this one. The theory of cosmic inflation, the extraordinarily rapid inch expansion that physicists believe occurred in the first fraction of a second after the Big Bang, was developed to explain several otherwise puzzling features of the observable universe. Its remarkable uniformity on large scales, its near perfect spatial flatness, and the specific statistical pattern of the cosmic microwave background fluctuations. The theory works. The Planck satellite's detailed measurements of the cosmic microwave background are consistent with inflationary predictions in detail that would be impossible to replicate with a different model. Most physicists who work on early universe cosmology accept inflation as the most promising framework for understanding the universe's initial conditions. But inflation has an uncomfortable consequence. In most versions of inflationary theory, the rapid expansion does not stop uniformly everywhere at the same moment. Quantum fluctuations cause it to stop in some regions, which become bubble universes, each beginning a new era of ordinary expansion, while inflation continues indefinitely elsewhere. This process, called eternal inflation, generates a potentially infinite number of bubble universes, each causally disconnected from the others, each with its own quantum initial conditions. Some of those bubble universes may have different values of the fundamental constants of physics, different masses for the electron, different strengths of electromagnetism, different values of the cosmological constant. Most of them may be radically inhospitable to anything we would recognize as structure or life. A small fraction may resemble ours closely. The total number of bubble universes produced by eternal inflation, if the theory is correct, is likely infinite. There is, in principle, no mechanism that produces a finite number. We cannot observe any of these other universes. They are causally disconnected from ours. But the mathematics of the most successful theory of our universe's origins points inexorably toward them. As you close your eyes tonight, you carry the universe with you, not poetically, literally. The hydrogen in the water in your cells was made in the first 3 minutes after the Big Bang. It is 13.8 billion years old. The carbon in your DNA was synthesized in the helium-burning core of a star that died before the sun was born. The oxygen you breathe was made in nuclear-burning reactions in massive stars and scattered by their explosions. The calcium in your bones came from supernovae. The iron in your blood was forged in the collapse of a star's core in a moment of such extreme physics that the energy released in 10 seconds exceeded what the sun will radiate over its entire 10 billion year lifetime. You are not separate from the universe. You are a local organization of it, a temporary, local arrangement of matter and energy that the universe has been assembling for billions of years from the raw materials the Big Bang provided and the stars enriched. Every atom in you has a history that predates the Earth by billions of years. Every atom will outlast you by billions more. After your body has returned its atoms to the soil and the atmosphere and the ocean, those atoms will continue their journey into plants, into other animals, into the geological cycles of rock and sea, eventually, perhaps, into the interstellar medium when the sun finally exhausts itself billions of years from now and the Earth's material is returned to space. You are not a visitor to the universe. You are a temporary pattern within it, made from it, thinking with it, wondering about it. The universe examining itself through the particular arrangement of atoms it has assembled here, in this moment, in you. This is what the science says, stated plainly, not as mysticism, as chemistry and physics and cosmology. The universe is in this room tonight, in the walls, in the air, in the cosmic microwave background, passing silently through everything, in the dark matter flowing through the floor and through you at hundreds of kilometers per second, in the atoms that make up your body and carry within them the histories of dead stars. You are a very small and very organized piece of a very large and mostly disorganized universe. And from somewhere within that small organized piece, something is happening that does not happen in the vastness of the empty cosmos around it. Wondering, and now it is time to rest. The universe will continue its work while you sleep. Stars will fuse hydrogen in their cores. Somewhere, a supernova will scatter the elements of a new planetary system into an interstellar cloud. Somewhere, a molecular cloud will collapse and ignite a new star. Somewhere, two black holes, spiraling toward each other for millions of years, will complete their final merger in a burst of gravitational waves that will reach Earth in a few 100 million years. None of it requires your attention. None of it pauses for you or for any of us. The universe has been running continuously for 13.8 billion years, and it will continue long after tonight. But you, right now, in this particular arrangement of atoms, in this particular place, at this particular moment, you are part of it, not a spectator, not a visitor, a participant, made of it, running on its energy, thinking with its matter. Let that thought carry you gently towards sleep. The stars will still be there. The ancient photons will still be flowing. The dark matter will still be passing through, silent and everywhere, holding the galaxy together while you dream. Good night. Rest well. The universe will be here in the morning. There is a type of galaxy that eats other galaxies and leaves almost no trace. The Milky Way is not a solitary structure. It exists within a small collection of galaxies called the local group, bound together by gravity, occupying a region of space approximately 10 million light years across. The local group contains two large spiral galaxies, the Milky Way and Andromeda, and dozens of smaller companions, mostly dwarf galaxies orbiting the two giants. The large galaxies do not simply coexist with their smaller companions. They consume them. When a dwarf galaxy wanders too close to the Milky Way, the gravitational difference between the near side and the far side, the tidal force, begins to stretch and distort it. Stars on the side closer to the Milky Way feel a stronger gravitational pull than stars on the far side. Over millions of years, the dwarf galaxy is elongated into a stream of stars wrapped around the orbit of its larger neighbor, its material gradually absorbed into the Milky Way's halo. This process is called tidal disruption and is not rare. The Sagittarius dwarf galaxy, currently in the process of being disrupted, has been identified as a stream of stars wrapped around the Milky Way, its material already distributed across a vast arc of the sky. The Gaia satellite's data revealed that the Milky Way experienced a major merger approximately 8 to 10 billion years ago that contributed significantly to the structure of the stellar halo we see today. The Milky Way is in part made of consumed galaxies. Their stars persist, orbiting now as members of our own galaxy, their original membership recorded only in the subtle statistics of their chemical compositions and orbital energies. There is a form of radiation produced by the vacuum itself. The vacuum of space is not truly empty. Quantum mechanics demands that even in the absence of any matter or radiation, the electromagnetic field and all other quantum fields cannot be in a state of zero activity. Quantum fluctuations, temporary appearances of particle-antiparticle pairs that annihilate almost immediately, occur continuously throughout all of space. In most situations, these fluctuations have no directly observable effect, but near the event horizon of a black hole, they become significant. Stephen Hawking showed in 1974 that the intense curvature of space-time near an event horizon can separate a virtual particle-antiparticle pair before they can annihilate. One particle falls into the black hole, the other escapes. The escaping particle carries real energy, which must come from somewhere, and it comes from the black hole itself. The black hole loses a tiny amount of mass with each such event. This is Hawking radiation. It is so faint that it has never been directly detected. The temperature of the Hawking radiation from a stellar mass black hole is approximately 60 billionths of a degree above absolute zero, far below the temperature of the cosmic microwave background and undetectable by any current instrument. But the physics is well founded, and the principle is supported by theoretical work from multiple independent approaches. Over the immense timescales of the universe's far future, after all the stars have burned out and the cosmic microwave background has cooled to a billionth of a Kelvin, Hawking radiation will become significant. Black holes will slowly evaporate, radiating away their mass over timescales that dwarf the current age of the universe by factors incomprehensible to ordinary arithmetic. The last black holes, the most massive ones, will take approximately 10 to the 100th power years to evaporate completely, 10 with 100 zeros after it. After that, nothing remains with mass or structure. The universe will be an extremely cold, extremely dilute gas of photons and other massless particles, expanding forever, approaching but never reaching the silence of absolute zero. There is a phenomenon called gravitational lensing that allows us to see around corners. Light travels in straight lines through empty space, but space is not always empty of mass, and mass curves space, and curved space curves the path of light traveling through it. When light from a distant galaxy passes through the gravitational field of a massive foreground object, a galaxy cluster, a large elliptical galaxy, even an individual massive star, its path is bent by the curvature of space-time. The result is that the distant galaxy can appear distorted, stretched, multiplied, or amplified by the foreground mass acting as a lens. Einstein predicted this effect in 1915 and calculated the deflection angle for light passing the sun, approximately 1.75 arc seconds. This was confirmed during the total solar eclipse of 1919 by Arthur Eddington and his collaborators, who measured the positions of stars near the edge of the eclipsed sun and found them displaced exactly as Einstein's theory predicted. The result made Einstein internationally famous overnight. Gravitational lensing on cosmological scales produces some of the most striking images in astronomy. The Hubble Space Telescope has photographed galaxy clusters surrounded by luminous arcs, images of background galaxies stretched into curves and arcs by the lens. In some cases, the same background galaxy appears multiple times around the lens, its image duplicated by the geometry of the lensing. In the most perfect alignments, the background source, The lens and the observer line up exactly, and the lensed image appears as a complete ring of light surrounding the lens, an Einstein ring named after the physicist whose equations predicted it. These rings are not common, but they have been observed. The universe allows us to see objects that would otherwise be far too faint and far too distant to detect. The massive structures between us and the farthest reaches of the observable universe act as natural telescopes, magnifying and amplifying light from beyond. Some of the most distant galaxies ever observed were found because gravitational lensing had magnified them to detectable brightness. There are objects in the universe that are simultaneously very old and very bright. Quasars, quasi-stellar objects, were first identified in the 1960s as point-like radio sources with unusual spectra. Their brightness was extraordinary, but their spectra showed redshifts, implying they were enormously distant. When astronomers calculated how bright they would need to be to appear as bright as they did from such great distances, the numbers were staggering. Some quasars are more luminous than an entire galaxy of hundreds of billions of stars. The explanation took years to establish. A quasar is the active nucleus of a distant galaxy, a region surrounding a supermassive black hole in the process of actively consuming surrounding matter. As gas falls toward the black hole, it forms an accretion disk, a flat rotating structure of superheated gas that glows with enormous luminosity across the electromagnetic spectrum. A fraction of the infalling material is ejected as powerful jets perpendicular to the accretion disk, beaming energy across millions of light years. At peak luminosity, the most powerful quasars outshine their host galaxies by a factor of 1,000 or more. From across the observable universe, they are visible as the brightest persistent objects in the cosmos. The most distant quasars are seen as they were when the universe was less than 1 billion years old. They harbor black holes with masses of 1 billion solar masses or more, black holes that grew to enormous sizes astonishingly quickly, posing a puzzle for theories of black hole growth. How did they become so massive so fast? The answer remains incompletely understood. The Milky Way's own central black hole, Sagittarius A star, is currently quiet. It consumes very little material compared to an active quasar. But the evidence suggests that the Milky Way was itself an active quasar billions of years ago when its central black hole was feeding vigorously. The galaxy we inhabit was once one of the brightest objects in the observable universe. There are stars that will burn for longer than the universe has existed 1,000 times over. Red dwarf stars, stars with masses between approximately 8% and 50% of the sun's mass, are the most common type of star in the Milky Way. They make up approximately 70 to 80% of all stars. They are also extraordinarily long-lived. A red dwarf with a mass of approximately 10% of the sun's mass fuses hydrogen so slowly that it can remain on the main sequence for approximately 10 trillion years. 10 trillion years is approximately 720 times the current age of the universe. Unlike more massive stars, its red dwarfs are fully convective. The material in the star is constantly circulated throughout the stellar volume by convection, bringing fresh hydrogen from the outer layers to the core. This means they can use nearly all of their hydrogen as fuel, not just the hydrogen in the central core. Their longevity is extreme. When the current generation of stars in the Milky Way has exhausted itself, when the sun has expanded and died, when the most massive stars have exploded and their remnants have cooled, the red dwarfs will still be burning. They will outlast every other class of star by enormous margins. The last red dwarf star will burn out approximately 10 trillion years from now, leaving a white dwarf remnant that will cool slowly over the following trillions of years. For most of the stelliferous era, the age of starlight, the universe will be dominated not by stars like the sun, but by these dim, small, patient red embers. There is a number that represents the total amount of starlight ever produced in the history of the universe. It is not easy to calculate. Stars have been forming and dying since approximately 200 million years after the Big Bang. The rate of star formation has varied enormously over cosmic time, rising steeply in the first few billion years, peaking approximately 10 billion years ago, and declining slowly since. By integrating the star formation history of the universe and accounting for the luminosity of stars over their lifetimes, astronomers have estimated the total photon production of the universe. This number is the extragalactic background light, the cumulative optical and near infrared glow of all the stars that have ever existed. A paper published in 2018 in Science by Marco Agello and colleagues, using data from the Fermi Gamma Ray Space Telescope, measured the optical infrared background light by observing how high energy gamma rays from distant blazars are attenuated by their interactions with these background photons. The measurement allowed them to reconstruct the total photon content of the universe from the epoch of the first stars to the present. They found that the universe has produced approximately 4 times 10 to the 84th power photons of optical and near infrared light since the first stars formed. That is a 4 followed by 84 zeros. All of those photons are still in the universe. They have not disappeared. They have been stretched by cosmic expansions into infrared and then into longer wavelengths. Some have been absorbed, but many continue traveling, filling the universe with a diffuse background glow, invisible to the naked eye, but detectable with sensitive instruments. Every photon ever produced by every star that has ever burned is still somewhere in the universe, still traveling, still carrying the energy of the nuclear fusion that created it. There is a connection between the chemistry of life and the death of stars. The synthesis of heavy elements in stars is not merely a fact of nuclear physics. It is the foundation of chemistry, geology, and biology on every planet that has ever formed with the right conditions for life. The Big Bang produced hydrogen, helium, and traces of lithium and beryllium. That was the complete chemical inventory of the young universe. Every element heavier than beryllium that exists anywhere in the cosmos, the carbon and nitrogen and oxygen of biology, the silicon and iron and magnesium of geology, the gold and uranium and lead of heavy metal chemistry, was produced by nuclear reactions inside stars, or in the extreme conditions of stellar deaths. Carbon is synthesized in the helium burning phase of red giant stars through the triple alpha process. 3 helium nuclei combining into a single carbon nucleus in a reaction so improbable that it requires a resonance in the carbon nucleus at exactly the right energy. In 1952, Fred Hoyle predicted this resonance must exist because carbon obviously exists and because this reaction is the only plausible way to make it. The resonance was subsequently found in laboratory measurements exactly where Hoyle predicted. It is one of the most remarkable examples of scientific reasoning in the history of physics. The nitrogen in amino acids was made in carbon-nitrogen-oxygen cycle reactions in massive stars. The oxygen in water was made in the same helium-burning shells that produce carbon, as well as in more massive stars during carbon burning. The phosphorus in DNA was made in supernova explosions. Life is not a chemical accident on a planet that happened to have the right conditions. Life is the product of 13 billion years of stellar nucleosynthesis, billions of stars living and each generation enriching the interstellar medium with heavier and more complex elements until there was enough carbon and oxygen and nitrogen and phosphorus to build the molecules of biology. The stars did not make life, but they made everything life is made of. There is a property of black holes that suggests they remember everything. When an object falls into a black hole, its atoms, its information, its structure, everything it was, crosses the event horizon and is, from the perspective of an outside observer, gone. The black hole gains mass, angular momentum, and electric charge. That is all an outside observer can measure. This simplicity is captured in the saying that black holes have no hair, a phrase attributed to John Wheeler, meaning that a black hole is characterized by only three quantities: mass, spin, and charge. It does not matter whether the black hole formed from the collapse of a star made of iron, or from the collapse of a star made of carbon, or from the infall of a library of books. The result is the same, but information in physics is supposed to be conserved. The laws of quantum mechanics are reversible. If you know the exact quantum state of a system at one time, you can in principle calculate its exact state at any other time. Information is never truly destroyed. If information is lost when matter falls into a black hole, then the laws of quantum mechanics are violated. This is the black hole information paradox, first identified by Stephen Hawking, and it remains unresolved. Recent work, particularly calculations by physicists including Ahmed Almheiri, Juan Maldacena, and others, suggests that information is not actually lost, that it is somehow encoded in the Hawking radiation emitted by the black hole over its lifetime, in correlations between the emitted particles that would, in principle, allow the original quantum state to be recovered. The mechanism by which this happens is not fully understood, but the growing consensus among theoretical physicists is that quantum mechanics is not violated. The information escapes, somehow carried by the radiation. The universe, at its deepest level, may forget nothing. There is a type of supernova so powerful it destroys the star completely. In ordinary core collapse supernovae, when a massive star exhausts its nuclear fuel and its core collapses, the explosion destroys the star's outer layers and leaves behind a neutron star or black hole. The remnant is compact and hot, glowing for thousands of years as it expands. But some supernovae are driven by a different mechanism that leaves nothing behind. When a star with more than approximately 130 times the mass of the Sun reaches the end of its life, the conditions in its core can become extreme enough that pairs of particles and antiparticles, electrons and positrons, spontaneously form from the intense radiation field. This reduces the radiation pressure supporting the star, causing a partial collapse that triggers explosive nuclear burning. In some cases, the explosion is so energetic and the nuclear burning so complete that the entire star is obliterated. No neutron star, no black hole, nothing. Just an expanding cloud of gas and radiation. These events are called pair instability supernovae. They have been observed. In 2007, astronomers detected an event designated SN 2007 by, which showed characteristics consistent with a pair instability supernova from a star initially approximately 200 solar masses. The iron produced in such a supernova, and these events produce enormous quantities of iron and other heavy elements, is scattered into the interstellar medium without any compact remnant left behind. The star disappears completely. Its entire mass becomes the interstellar medium available for the next generation of stars and planets. Everything you see tonight when you look at the sky is inside the Milky Way. This is not quite accurate. The Andromeda Galaxy is visible to the naked eye as a faint smudge in the constellation Andromeda, and under very dark skies, a few other nearby galaxies can be glimpsed. But everything you see as individual stars, every named star in every constellation, every bright point that makes up the pattern of the night sky, is inside our own galaxy. The most distant star visible to the naked eye under ideal conditions is a blue supergiant in the constellation Cassiopeia, approximately 16,000 light years away. That is 16,000 light years within a galaxy, 100,000 light years across. We are seeing, with unaided eyes, only the nearest fragment of the Milky Way's stellar population. The vast majority of the Milky Way's 2 to 400 billion stars are invisible to us without a telescope, obscured by distance and by the dust and gas that fills the galactic plane. When we look toward the center of the galaxy, toward the constellation Sagittarius, we see the glow of billions of stars blended together into the bright band of the Milky Way. What we cannot see is the central bulge, hidden behind approximately 30 magnitudes of visual extinction from intervening dust, a dimming factor of approximately a trillion. The galaxy we inhabit is a place of immense scale. The night sky shows us a tiny portion of it. The rest is there, behind the dust and the distance, containing most of the galaxy's stars, most of its star-forming regions, and at its very center, the 4 million solar mass black hole around which everything ultimately orbits. As you drift towards sleep, the night is full of things you cannot see. Gravitational waves are passing through this room right now, produced by binary neutron stars, merging black holes, and possibly other sources. These ripples in space-time propagate at the speed of light in all directions. Every merger event anywhere in the observable universe sends waves outward. Some of those waves are arriving here, stretching and squeezing the distance between any detachment by amounts incomprehensibly small, on the order of 1,000th the diameter of a proton per kilometer of separation. The LIGO and Virgo detectors can measure these distortions with extraordinary sensitivity, but the detectors must be kilometers long, isolated from vibration, cooled to minimize thermal noise. This room is too small and too noisy. The waves pass through undetected. Neutrinos from supernovae that exploded in distant galaxies billions of years ago are passing through. Cosmic rays from the remnants of stars that died before the sun formed are arriving, some of them striking atoms in the atmosphere above and producing showers of secondary particles that reach the ground. Dark matter particles are flowing through the floor and the walls and your body in the millions per square centimeter per second. The universe is not inactive while you rest. It is intensely, continuously, energetically active at every scale from the quantum to the cosmological. Everything is happening all at once, everywhere, all the time. You are surrounded by processes of extraordinary complexity and scale, most of them entirely invisible to human senses. And through all of it, here you are. One small, temporary, organized arrangement of ordinary matter, aware, resting, connected to all of it by the atoms that make you up and the physics that runs through everything. Let the universe do its work tonight. It does not need your help. Sleep well. The questions will be here in the morning. The stars will be here in the morning, and so will you. Good night. There are galaxies so large that our entire local group would fit inside them with room to spare. The Milky Way has a diameter of approximately 100,000 light years. The Andromeda Galaxy is slightly larger, approximately 220,000 light years across. Together with dozens of smaller companions, these two spiral galaxies dominate the local group, a collection of galaxies bound by gravity and occupying a region roughly 10 million light years across. IC 1101 is a different kind of galaxy entirely, located approximately 1 billion light years away in the constellation Virgo. It is a supergiant elliptical galaxy at the center of the Abell 2029 galaxy cluster. Its diameter is estimated at approximately 5.8 million light years. The entire local group, the Milky Way, Andromeda, and all their smaller companions spread across 10 million light years, could fit inside Psi 1101 with room remaining. IC 1101 contains approximately 100 trillion stars. The Milky Way contains perhaps 2 to 400 billion. IC 1101 has approximately 2 to 500 times more stars. How did such a structure form? Giant elliptical galaxies like IC 1101 grow primarily by consuming smaller galaxies. Over billions of years, the gravitational influence of the massive central galaxy draws in smaller companions, which are disrupted and absorbed. Each merger adds mass, scatters stars into a smooth ellipsoidal distribution, and contributes to the growth of the central object. IC 1101 is, in some sense, the record of many galaxies, hundreds of them absorbed and blended over cosmic time into a single enormous structure. What was once a diverse collection of individual galaxies with their own histories is now a single smooth ellipsoid, its past mergers written only in statistical signatures of its stellar populations. There is a star that has a composition unlike almost any other in the Milky Way, HD 192263. A subgiant star approximately 320 light years from Earth has a peculiarly high abundance of barium relative to iron and other elements. Stars with unusual heavy element abundances are sometimes products of mass transfer in binary systems. Material transferred from a companion star that was once an asymptotic giant branch star, a phase of stellar evolution in which the slow neutron capture process produces many of the heavy elements beyond iron. But more dramatically, astronomers have identified stars called carbon-enhanced metal-poor stars, stars with very low overall heavy element content, but unusually high abundances of carbon, nitrogen, oxygen, and S-process elements. These stars appear to carry the chemical fingerprints of the very younger generation of massive stars. Population 3 stars, which are believed to have produced these abundance patterns in their nuclear burning and supernova nucleosynthesis. These chemically unusual stars are among the most valuable objects in observational astronomy. By analyzing the detailed pattern of their element abundances, astronomers can constrain the properties of the first stars. Their masses, their explosion energies, the temperatures and densities in their interiors during nucleosynthesis. The first stars are all long dead. No direct observation of them is possible with current technology. But their chemical legacy persists in the atmospheres of some of the oldest surviving stars, a message written in the ratios of elements, transmitted across 13 billion years, waiting to be read by anyone patient enough to take a spectrum. There is a concept in physics called the Planck length, and it may be where space stops being smooth. The Planck length is approximately 1.6 times 10 to the minus 35 power meters. It is derived from three of the most fundamental constants in physics: the speed of light, Planck's constant from quantum mechanics, and the gravitational constant, on length scales larger than the Planck length, which includes every scale that has ever been directly measured or observed. Space appears smooth and continuous. General relativity treats spacetime as a perfectly smooth four-dimensional manifold. Quantum field theory treats space as a backdrop against which quantum fields propagate without discreteness at accessible scales. But some approaches to quantum gravity, the as yet incomplete attempt to unify general relativity with quantum mechanics, suggest that below the Planck length, the smooth fabric of space-time breaks down. Space may have a granular structure at this scale, more like a network or a foam than a smooth continuum. Distance below the Planck length may not be a well-defined concept in a complete theory of quantum gravity. If this is correct, the Planck length is the smallest possible measurement, the universe's fundamental pixel. Space is not infinitely divisible. It has structure all the way down to a scale so small that no instrument conceivable within current physics could probe it. The implications would be profound. It would mean that the equations of general relativity, which assume a smooth space-time, are an approximation, accurate at all scales we can probe, but breaking down in the extreme. It would mean the universe has a discrete structure at its foundation, beneath the smoothness of everything we can observe. Whether this is true is not known. It is one of the deepest open questions in theoretical physics. There are objects in the universe that rotate so fast their surfaces move at a significant fraction of the speed of light. The fastest spinning pulsars, neutron stars that emit beams of electromagnetic radiation observed as regular pulses as they rotate, are called millisecond pulsars. They are believed to have been spun up by accreting material from a companion star over millions of years, gradually increasing their rotation rate until they reach extraordinary speeds. The record holder as of current measurements, Poor J 1748 minus 2446, completes approximately 716 rotations per second. Its circumference is approximately 125 kilometers. At the equator, the surface of this neutron star is moving at approximately 24% of the speed of light, roughly 72,000 kilometers per second. The centrifugal effects at this rotation rate are enormous. The star's equator bulges outward relative to its poles. The gravitational field at the equator is slightly reduced compared to the poles. The space-time around the rapidly rotating star is dragged along with it in a phenomenon called frame dragging, a prediction of general relativity observable in the orbits of other objects in the vicinity. These millisecond pulsars are extraordinarily stable timekeepers. Their rotation rates, while very high, are also remarkably constant, declining at rates of nanoseconds per day due to the gradual radiation of energy as electromagnetic waves. Arrays of millisecond pulsars can be used as detectors for gravitational waves with frequencies in the nanohertz range, longer period gravitational waves than those detected by LIGO, produced by supermassive black hole binaries in distant galaxies. The universe uses its most extreme objects as tools for its own measurement. There is a boundary in the universe beyond which we can never send information. The cosmic event horizon is not the same as the boundary of the observable universe. The observable universe is defined by how far light has had time to travel since the Big Bang, approximately 46.5 billion light years. But the event horizon is defined by how far light emitted today can travel before the accelerating expansion of the universe outruns it. Because dark energy is causing the expansion to accelerate, objects beyond a certain distance are receding from us at faster than the speed of light. Not because they are moving through space faster than light, but because the space between us and them is expanding. Any light we emit today, traveling outward at the speed of light, will never catch up to objects beyond the event horizon because those objects are being carried away faster than the light can close the gap. The current distance to the cosmic event horizon is approximately 16 billion light years. Objects beyond this distance today cannot be affected by any signal we send now. Conversely, light emitted by objects beyond this distance today will never reach us. Those objects are crossing our event horizon as we observe them from the past. This means the observable universe, while already vast beyond ordinary comprehension, is actually larger than the universe we can interact with. Information sent today can only ever reach objects within 16 billion light years. Everything beyond that is outside our causal future. As dark energy continues to accelerate the expansion, the event horizon will slowly contract. Fewer and fewer of the universe's regions will be reachable by any signal from Earth. The universe is not only expanding, it is, from our perspective, slowly closing. There are objects called magnetars with magnetic fields trillions of times stronger than anything on Earth. Earth's magnetic field at the surface is approximately 5 times 10 to the negative 5 Tesla, strong enough to deflect a compass needle. weak enough to be completely undetectable without sensitive instruments. It is generated by electrical currents in the planet's liquid iron core. A magnetar is a neutron star with an extraordinarily strong magnetic field generated during its formation by rapid rotation and complex currents in the dense neutron fluid of the stellar remnant. Magnetar magnetic fields reach approximately 10 to the 11 power Tesla, 100 billion Tesla. Earth's field is approximately 5 times 10 to the negative 5 Tesla. The ratio is approximately 2 times 10 to the 15, 2 quadrillion times stronger. At that field strength, the vacuum of space itself becomes polarized. The force on a charged particle near a magnetar is so enormous that atomic nuclei are deformed, stretched into elongated shapes along the field lines, quite unlike the spherical nuclei found in ordinary matter. The chemistry and even the structure of matter near a magnetar is fundamentally different from anything accessible to laboratory physics. Magnetars occasionally undergo starquakes, sudden rearrangements of their crystalline crust that release enormous bursts of energy as gamma rays and X rays. A magnetar flare on December 27, 2004, was bright enough that, despite originating 50,000 light years away, it briefly disrupted Earth's ionosphere. For approximately a tenth of a second, the most energetic event in recorded human history was a gamma ray burst from a dead star on the other side of the Milky Way. And now, once more, it is time to rest. The universe does not require your awareness to continue. It has been running without witnesses for most of its 13.8 billion year history. The first stars formed without any eyes to see them. The first galaxies assembled without any mind to contemplate them. The first planets formed and cooled and, on at least one of them, evolved complexity, and that complexity eventually developed the capacity to look back at all of it. You are a very recent development in a very old story. The story will continue after you, and after everyone alive tonight, and after the human species itself, which is only a few 100,000 years old in a universe nearly 14 billion years old, and which will not exist in its current form forever. But right now, in this moment, the story includes you. Your awareness is part of the universe's awareness of itself. The atoms that make up your brain are thinking about the atoms in distant stars. The matter that will eventually return to the interstellar medium is, right now, contemplating the interstellar medium. This is not mysticism. It is physics stated plainly. You are made of the same stuff as the universe, governed by the same laws, continuous with it in space and in time. The boundary between your body and the cosmos is useful for daily life, but does not correspond to any fundamental physical division. Let that thought be peaceful if it can be. You are not separate from the vast, dark, ancient, expanding cosmos. You are inside it, made of it, part of its current inventory of organized matter, temporarily assembled into a form that wonders. And now that form is resting. The stars are doing what stars do. The dark matter is flowing through the walls. The ancient photons of the cosmic microwave background are filling this room with 2.7 degrees of warmth from the beginning of time. The universe will be here when you wake. Good night. There is a type of binary star system where two white dwarfs orbit each other in less than an hour. White dwarfs are the dense, cooling remnants of stars that have exhausted their nuclear fuel and shed their outer layers. They are typically about the size of Earth, but with a mass comparable to the Sun. In most cases, they cool slowly over billions of years, gradually dimming from white to yellow to orange, orbiting their original companions, if any remain, or drifting alone through the galaxy. But some white dwarfs exist in extraordinarily tight binary systems, pairs of white dwarfs orbiting each other in orbits so small that their orbital period is less than 1 hour. These systems are called AM Canum Venaticorum systems, or AMCVN stars, and they involve two white dwarfs so close together that matter can flow from one to the other through a process called Roche-Lobe overflow. In these systems, the two stars are separated by only a few tens of thousands of kilometers, less than the radius of the Sun. They orbit each other in minutes, sometimes in less than 10 minutes for the most extreme cases. As they orbit, they emit gravitational waves continuously. Their rapid orbital motion and close separation makes them among the strongest expected sources of gravitational waves in the millihertz frequency band. Future space-based gravitational wave detectors, like the proposed LISA mission, should be able to directly detect the gravitational wave emission from these systems. Some known AMCVN systems will serve as verification sources, objects whose gravitational wave signals can be predicted from electromagnetic observations, providing a direct test of the detector's performance. In less than an hour, two dead stars complete a full orbit of each other, bleeding gravity into space, drawing closer with every year, ultimately destined to merge or trigger a thermonuclear explosion that will briefly remake them as a single, violently different object. There is a region of the sky where the first stars ever formed might finally become visible. The epoch of reionization is the name given to a period in the early universe, from approximately 200 million years to 1 billion years after the Big Bang, during which the first stars and galaxies formed, and their radiation ionized the neutral hydrogen gas that had filled the universe since recombination. Before the first stars ignited, the universe was in what astronomers call the cosmic dark ages. There were no stars. There was no light except the cooling remnant of the Big Bang, the infrared and microwave background growing dimmer and redder as the universe expanded. Hydrogen and helium drifted in the dark, slowly being drawn together by gravity into the first proto-galaxies, the first concentrations of matter dense enough to collapse into stars. When the first stars ignited, they were, theories suggest, different from any star alive today. They formed from gas containing essentially no heavy elements, only hydrogen and helium. Without the heavy element coolants that help modern molecular clouds fragment into smaller pieces, the primordial gas clouds probably collapsed into very massive objects, stars of perhaps 100 to 1,000 solar masses. These population, three stars burned hot and fast, lived only a few million years, and died in enormous explosions that scattered the first heavy elements into the universe. No population 3 star has ever been directly observed. They are too old and too distant. But the James Webb Space Telescope, launched in December 2021, is designed specifically to observe the earliest galaxies, the systems that formed in the epoch of reionization. Its infrared sensitivity and large mirror allow it to detect light from galaxies that existed when the universe was only a few 100 million years old. Those early galaxies contain the chemical signatures of the first stars. The spectra of their light tell the story of what was synthesized before them. By reading that story, we are reading the first chapter of stellar evolution, a chapter that has never been directly read before. There are moons in the solar system that may be among the most habitable environments we know of. Habitability is not the same as hospitability. Most of the solar system is intensely hostile to life as we know it. But habitability, the presence of conditions that might support life, extends beyond Earth in several compelling ways. Europa, the fourth largest of Jupiter's 67 known moons, has a surface of water ice. Beneath that ice, perhaps 10 to 30 kilometers below the surface, is a global ocean of liquid water, kept from freezing by tidal heating. Jupiter's enormous gravity flexes Europa's interior as the moon orbits, generating heat through friction. The resulting ocean may be 2 to 3 times the total volume of Earth's oceans. Evidence for this ocean comes from multiple sources. The paucity of impact craters on Europa's surface, suggesting the ice is young and constantly refreshed. The magnetic field measurements by the Galileo spacecraft, which found evidence of an electrically conductive layer beneath the surface consistent with a saltwater ocean, and the complex surface geology, including features called chaos terrain, where large sections of ice appear to have been disrupted by underlying liquid. Enceladus, a small moon of Saturn, provides even more direct evidence. The Cassini spacecraft detected active geysers erupting through cracks in the south polar ice, spraying water vapor, ice particles, and organic molecules into space. The source is a liquid water ocean beneath the ice. The organic molecules detected include complex hydrocarbons and molecular hydrogen, the latter suggesting ongoing hydrothermal activity at the ocean floor, similar to the hydrothermal vents on Earth that support rich ecosystems independent of sunlight. On Earth, life exists in hydrothermal vents at the ocean bottom, in ice, in acid, in radiation intense environments previously considered sterile. The definition of habitable is constantly being revised as we discover life in more extreme conditions. Enceladus and Europa may be, right now, the most promising locations in the solar system beyond Earth for the existence of microbial life. As the night deepens and sleep approaches, the universe continues its patient inventory. Somewhere tonight, a star is exhausting the hydrogen in its core for the last time before beginning its red giant expansion. The process takes millions of years. The star does not know. Its thermostat simply responds to physics. Somewhere tonight, a cloud of gas and dust, compressed by the passage of a nearby supernova shock wave, has reached the density threshold for gravitational collapse. In a few 100,000 years, it will ignite as a new star, perhaps surrounded by a planetary system. Somewhere tonight, two neutron stars that have been spiraling toward each other for hundreds of millions of years are approaching the final moments before their merger. The gravitational waves from that event will travel outward at the speed of light and arrive at Earth in some distant future, recorded perhaps by instruments not yet built. None of these events require a witness. None of them pause or change because of the presence or absence of any observer. The universe is indifferent in the precise sense that physics uses the word indifferent, not cruel or cold, simply operating according to its own rules without reference to anything external. And in the middle of all of this indifference, the extraordinary thing has happened that awareness exists. That matter has organized itself here on this planet and perhaps elsewhere too, into configurations that look back at the universe and experience something: curiosity, wonder, the feeling of significance at the scale of things. Whether that experience matters to the universe is a question physics cannot answer. Whether it matters to you is the only question that remains as sleep approaches. Let everything else go. The calculations can wait. The questions can wait. The universe will still be incomprehensibly large and mostly empty and mostly dark when you wake. For now, just rest. Good night. There is something called zodiacal light, and it is the dust of dead comets reflecting sunlight. On a very dark night, just before dawn in spring or just after dusk in autumn, a faint pyramid of light rises from the horizon along the path of the ecliptic, the band of sky through which the sun and planets move. This is the zodiacal light. It is not twilight. It is not aurora. It is something older and stranger. The zodiacal light comes from dust, specifically from tiny particles, typically between 10 micrometers and 1 millimeter in diameter, distributed through the inner solar system along the plane of the planet's orbits. These particles are the debris of comets that have passed through the inner solar system over millions of years, gradually shedding material with each pass near the sun, leaving a diffuse cloud of particles that follows the orbital plane. When sunlight strikes these particles, they scatter it. From Earth's surface, at night, when the geometry is right, we see this scattered sunlight as a faint, diffuse glow along the ecliptic, the ghost of ancient comets, their material still tracing the orbital plane long after the parent bodies have changed beyond recognition. The zodiacal light is the visible trace of the solar system's past. Every comet that has ever passed through the inner solar system has contributed to it. The dust accumulates over millions of years, is slowly pushed outward by radiation pressure and eroded by collisions, and is continuously replenished by new comets perturbed inward from the outer solar system by the gravitational influence of the giant planets. The faint light on the horizon before dawn is 4.5 billion years of comet passes, still visible, still reflecting the sun, still gently reminding the attentive observer that the solar system has a history of which tonight's sky is only the latest moment.